First, I would like to thank the organizers for keeping this excellent meeting and also inviting me to speak here. So I'm going to talk about many body localization in the presence of long-range interactions and long-range. Most of the work that I will discuss here has been done in collaboration with my students Abhishek. And these are the references. If time permits, I will also show some of the ongoing work. So this audience actually doesn't need any introduction on many body localization, but just for the sake of completeness, I'm going to spend a few minutes on it. So MBL is a very unusual phase of matter which is realized in interacting systems which are sufficiently disordered. It's a non-ergodic phase of matter, and that's why the local observables do not thermalize. The system retain memory of the initial state for a long time, and this is also reflected in area law behavior of entanglement entropy. So this is basically a recap of lectures on Monday. And so most of these properties you can explain in terms of local integrals of motion. And some of these unusual properties can also be very useful for us. For example, MBL can prevent heating in a periodically driven system and can also help us in realizing new phases of matter like time crystals. So MBL in experiments, of course, MBL has been realized in optical lattice experiments. So here I'm showing plots from the experiment from Emanuel Bloch's group, where it was realized in a model of for interacting fermions in quasi-periodic optical lattice. So, and how MBL is diagnosed experimentally. So you basically prepare your system in a initially charged density wave state and look at the relaxation dynamics of this initial state. So if the disorder is weak, your evolution is pretty ergodic, and the system loses the memory of the initial state very quickly. But beyond certain strength of disorder, you see that the initial order always persists even at very long times. So the question that is important to my talk is, in what kind of systems MBL can exist? Okay, so of course you need disorder and interactions, but can we say something about the range of interactions? So theoretically, it has been well established that if you have disordered one-dimensional chains with short-range interactions, we do have MBL. Most of the numerical work also focuses on one-dimensional short-range systems with disorder and have shown MBL to delocalization transition. But when it comes to the question of MBL in the presence of long-range interactions, there is a common belief that MBL does not exist in the presence of long-range interactions. And I guess the root of this belief goes back to what Anderson showed in his famous paper in 1958. So what Anderson showed is that if you have power law hopping in a disordered system, then basically the locator expansion breaks down if the power of this hopping alpha is less than or equal to d, where d is the dimension of the system. And this basically means that there is no localization in this system if you have long enough hopping, long range hopping. So let me just try to give you a very heuristic argument. So this is actually, I think a lot of things has been taken from paper by Sarang. So I guess that's why he's just finding it a bit funny. So, this is your Anderson model with power law hopping. So the resonance condition is, so a spin at site I can resonate with a spin at site J if this condition is satisfied, right? If the energy difference is less than or equal to this matrix element. So you can do a very simple exercise and try to get an estimate of the number of resonances within a sphere, d-dimensional sphere of radius r, if rho is the density of spins, and you see that this term diverges in the limit r going to infinity if alpha is less than d. Okay? So it means that any spin at site I can basically resonate with any other spin at very long distance, and you don't expect localization in this model for long range hopping. And there are generalizations of this argument for interacting systems, and people who are involved in this generalization, many of them are here in the audience. So if you now think of a system, this spin half system with both the terms being power law, and in general taking alpha not equal to beta, you can try to generalize this resonance count argument. So each resonant pair actually can provide a new pseudo-spin degree of freedom, and you can they can exchange energy with the help of this interaction term. So if you have two resonant pairs with a certain separation R2, you can repeat the exercise which we did earlier for the non-interacting case and try to get an estimate of the number of resonant pairs of these pseudo spins as a function of R1 and R2. As you see that now it depends on the powers beta as well as alpha. Now a very detailed description of various limits possible from this formula are given in this paper by 2014 PRL of Yao et al. And some of the limits were also discussed in this paper by Burin and other papers here. So basically what are the possible limits? You can fix size of one resonant pair, that is fixed R1, and take the limit R2 going to infinity. That is what I'm calling the small pair limits. And then you see that localization happens if your beta is larger than D. You can do another limit where you let the size of the resonant pair, you optimize the size of the resonant pair as you increase R2, and that gives you this extended pair limit. And then you can also keep iterating, creating these resonances, and that gives you the third limit. The important thing here to see is that there is a difference in the physics of system when you have these coefficients of power law terms random or non-random. Okay? So if these coefficients are random, then these are the different limits you can get. But if these coefficients are non-random, then you basically get a different limit because of the multiple expansion. But all these arguments are based on very few number of spins in your system, and also often you don't know which limit to believe. So, okay, so far so good. So what is the numerical status? So there's a lot of numerical work by Burin starting from 2016, maybe even before that, but it's impossible for me to summarize all of it here. But most of the conclusions from Burin's work are also consistent with what is shown in this paper. So I'm just going to show a summary of this paper, which basically says that if you have non-random, if you have random coefficients of these power law terms, and if you take alpha equal to beta case, then there is the critical disorder scales with the system size in a very interesting way, such that for alpha less than 2 for the one-dimensional case, the critical disorder becomes infinite in the thermodynamic limit, which means that for finite size system calculations, you might see a localization to delocalization transition in this system, but actually in the thermodynamic limit, there is no many-body localized phase in 1D as long as alpha is less than 2. There are some numerical work presented in this 2004 PRL of Yao, where again, so they looked at a different model. So now the coefficients of the power law terms are non-random, and alpha is equal to beta case. So they show that for alpha equal to 3, which is larger than 2, the system is delocalized, but for alpha equal to 1, system is completely localized. Sorry, the system is completely delocalized. So they predict the critical value of alpha to be somewhere between 1 to 3, where system should stop showing many-body localization. Okay, so you can see that this is not consistent with what was obtained from these simple resonant count pairs, because according to this, you will expect that if you have non-random coefficients, then you should see localization for alpha equal to 1 in 1D, but their numerical calculation actually showed delocalization for alpha equal to 1 in 1. There are other calculations where people have looked at only long range, like one of the exponents to be finite, the other one to be infinite, but there is no consistency as such. So what is the experimental situation? Why are we worried about thinking of many-body localization in the presence of long-range interactions? Do we have any real examples? Of course, most of the real systems we can think of have interactions which decay algebraically with distance and have disorders. So it's a very natural question to ask. What happens to MBL in the presence of long-range interactions? And in fact, in this very recent experimental work, a power law interaction between Ising spins was experimentally realized. The experiment was performed for alpha equal to 1.5, and by periodically driving this one-dimensional many-body localized phase, a time crystal phase was realized. So we do have examples from experiment that MBL persists in the presence of long-range interactions in 1D if you believe this experiment, but theory is not so consistent as far as the case of non-random interactions is concerned. Okay, so with this background, let me go to the model that I'm going to study. I'm going to look at model of spinless fermions again in one dimension, but not in the presence of fully random disorder, but in the presence of a deterministic aperiodic potential. And one of the reasons is that there are exponentially rare region effects which might make MBL unstable in the presence of power law interactions if you have random disorder. But in the presence of deterministic aperiodic potential, I don't expect such rare region effects to be present. So from that angle, we are safe. And another virtue of this model is that just by tuning the parameters in the model, you can analyze the limit where all the single particle states are localized or where you have a single particle mobility edge. The non-interacting limit of this model was first studied by Shmuel-Fishman long back in 1988. So for n equal to 1, it maps back to the Aubrey-Andre model, where all the states are delocalized for h less than 2t. For n between 0 to 1 and h less than 2t, the system has single particle mobility edges. For h greater than 2t, all the states are localized. And if you take larger values of n, all states are localized, and the localization length is equal to that of the corresponding random model. Okay, so we choose n to be between 0 to 1. Basically, we choose n to be half. And most of the results I will show you are corresponding to h much larger than this transition point, so that all the single particle states are localized. But I will show you some results also for h less than 2t, where we have single particle mobility edges. So actually, it's not becoming chaotic, because for n between 0 to 1 also, this has mobility edges. And if you take h larger than 2t, then all states are localized for all values of n. But if n becomes very large, then it becomes almost random. So this is just a non-interacting model with nearest neighbor hopping. These statements, so Shmuel-Fishman, the original work of Shmuel-Fishman is just with the nearest neighbor hopping with this aperiodic potential. Any doubt? Oh, sorry, I'm sorry. So it is non-interacting as well as nearest neighbor hopping. That's what discussed in these two papers. The focus of my work is I'm going to look at the effect of these power law terms on this model, and basically I will look at the effect of power law interaction and power law hopping separately, which means that either I will fix the limit alpha going to infinity with beta finite or vice versa, and we choose the parameters such that in the presence of nearest neighbor interaction and nearest neighbor hopping, the system is an infinite temperature MBL phase. And then you crank up the range of either the interaction term or the hopping term and ask the question, what happens to that MBL phase? Does it persist or not? I'm going to show you arguments in support of this observation that turning on long-range interactions does not delocalize the system. MBL persists even when alpha is less than 1, but turning on long-range hopping causes delocalization. Please note that I'm using non-random coefficient of this power law. So the first thing we do is we map this many-body model to the effective Anderson model in Fock space of the spinless fermions. So the local energy in the effective Anderson model gets contribution from all the from interaction among all the particles. So just one note. So I have rewritten my Hamiltonian in a little different form here so that I can use only one exponent alpha. So when I say I'm working with power law interaction system, it means my T1 is 0 and V1 is equal to V. And for the system with power law hopping, my V1 will be 0 and T1 will be equal. So you can, of course, map this many-body Hamiltonian to the effective Anderson model in Fock space, where your local energy gets contribution from the disorder term here and as well as from interaction among all the particles. And this TLM connects the different configurations in the Fock space, and it's basically coming from the hopping in the original model. So this is a non-interacting model, but of course it's not easy to solve it. And so now, just like in case of single particle localization, here also delocalization can be studied in terms of proliferation of resonances on the Fock space. One can identify resonant pairs on the Fock space configuration which satisfy this condition if the difference in energy of two Fock space configuration is less than or equal to the matrix element that connects it. And one can get an estimate of the number of resonant pairs by calculating these different terms of this series. So here, these summations with primes and double primes are important because it means that you have to exclude L here and M and L here, and so that you don't go to the same configuration and again and again. So this is equivalent to doing some kind of self-avoiding work on space. So one can get a probability distribution of the number of resonances. So we did calculation up to third order in the previous equation which I showed. Of course, you cannot calculate all the terms. So if you do the calculation up to third order, and these are the parameters for which I'm showing you the numerical results, you see if in the case of when the system has power law interactions, if you increase the range of interaction, nothing happens basically to the distribution of resonances. But if you look at the case when the system has power law hopping, the most probable value of the number of resonances increase when you increase the range of hopping. Here I have shown the most probable value of resonances. And just to see what happens when you go to one more order, higher order in interaction, because you don't see any change in the number of resonances, at least up to third order. But that doesn't mean that there cannot be any divergence in the number of resonances when you include all higher order terms. But even by changing the number, the order of calculation by 2, we don't see any change in the number of resonances. And here I have plotted the normalized number of resonances for the case of power law hopping. You can see that for alpha up to alpha equal to 2, it saturates when as a function. So this Vf is the volume of the Fock space. Up to alpha equal to 2, it saturates when you increase the volume of the Fock space. But for longer range hopping, it actually increasing monotonically with the volume of the Fock space, which means that in the thermodynamic limit, you expect diverging number of resonances in Fock space when your hopping is long enough in range. So this calculation just shows you that although we cannot conclude anything about whether there is going to be localization or delocalization in the case of power law interactions, but I can clearly say that there is going to be delocalization in case of power law hopping. And but as I show you other diagnostics, you will see that even this calculation is hinting that there is no delocalization in the case of power law interaction. Is there a question? No, but you're talking about the resonance calculation in the single particle space, right? Hmm? Due to interactions, yes. So that has already been done, right? So the interactions are already acting in your. In Fock space, it automatically comes in the local energy. Mm-hmm. Uh, well, I'm not saying that there are no resonances. I'm saying the number of resonances does not increase significantly when you increase the range of interest. That is probably because. Yes. So I guess the easy way to understand is just to look at this expression for the local energy, right? So even if you change the range of interaction here, you only change the distribution of this local energy very mildly. So if you think in terms of this Fock space, it's not very surprising that even when you have long range interactions, you really don't change the distribution of number of resonances significantly. I mean, there is of course a very minor increase, but no, I guess all that is already included in this Fock space picture, because my eventual if you look at the conclusion that the number of resonances don't diverge in the presence of long range interaction, it's actually consistent with your multiple calculation for the uniform interaction. So you do all that, and at the end when you use that you have uniform interaction, so you do get that for any beta positive, actually you will get no delocalization. Yes, 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 yes. So it is consistent with the real space calculation. Okay, so that's about the level spacing. Okay, sorry. So what I talked about is the number of resonances in Fock space, and now I will show you some data from exact diagonalization on this model. So the first and simplest thing to look is the level spacing statistics. So this is average ratio of the level spacings, and if you look at it as a function of this exponent alpha of the long range interactions and long range hopping, you can see that for all range of interaction, it remains close to the Poissonian limit, indicating that the system is localized. But if you have power law hops, then clearly for alpha less than 2, it approaches the Wigner-Dyson limit as you increase the system size. You expect, so this also indicates that the system delocalizes when you increase the range of hopping, and it is consistent with what we saw in the resonance count in Fock space. So let's do something more interesting. So one can prepare a CTW initial state and do a global quench and look at this imbalance. So if you look at the case of power law interactions, you don't see any power law decay in the imbalance. After this initial rapid decay, it very quickly saturates. And the saturation value is also not changing significantly when you change the range of interaction. But if you look at the case of when the system has power law hopping, see that for more than a decade, it actually decays as a power law. And this dynamical exponent increases as the range of hopping increases. Also, the saturation value decreases compared to what it is for the system with nearest neighbor hopping and nearest neighbor interaction, is the range of. One can also look at the entanglement growth. So again, this is the case for bipartite Renyi entropy as a function of time for the system which has power law interactions. You see for all values, for all ranges of interaction, you get this nice log T behavior. There is hardly any increase in the saturation value of the entanglement entropy. But if you look at the case with power law hopping, for very short time range, it looks like it behaves like a power law, but then the slope changes. So I'm not sure in this data whether we do have power log T behavior for the linear entropy or not. The saturation value definitely increases significantly as the range of hopping is. Okay, so so you see a clear difference between the entanglement growth in systems with power law interactions and power law hopping. But one has to see that if we start from this CDW initial state, of course we don't see a very clear signature which can tell me, okay, this is the critical value of alpha below which the system with power law interactions become delocalized, because it looks like there is a very minor change in the exponent and as well as in the saturation value. We looked at another initial state. So you can put all your particles in on the left corner of the system and prepare this one kink state. If you evolve this one kink state with respect to this Hamiltonian, then you see very drastic change between the system with power law interactions and power law hopping. For the case when you have power law interactions, the imbalance hardly changes. It just saturates very quickly to a value close to 1. And entanglement entropy also doesn't show any growth. But if you look at the system with power law hop, then you see very clear power law decays of the imbalance for a very long enough range of time. This exponent actually remains 0 within the error bar up to alpha equal to 2, and then it becomes non-zero. And the saturation value also decreases by more than 40% as you change the range of hopping. But the surprising thing is, so all these things indicate that the system is getting delocalized. But even in this delocalized system, you see pretty nice log T behavior of this entanglement entropy for a very broad range of time. For all values of alpha we have looked for. So this is something very surprising. So you generally won't expect log T behavior in a system which is so nicely delocalized. But so we were expecting some power law behavior in entanglement entropy, but seems that the system prefers to have a log T growth of entropy. Then we look at return probability. So again, you can see that if you have power law interactions, the return probability does not show any decay after the initial rapid decay, and it saturates very quickly. But if you have power law hop, you see these nice power law decays, and the dynamical exponent is non-zero and finite for alpha less than 2. And you also see the saturation value decreasing significantly as you increase the range of. The last thing is one can also calculate this density correlation function, which basically tells you if you create a density fluctuation at some site I at t equal to 0, how it evolves in time and space. And then from here you can calculate something like mean square displacement for the system. So if the system is diffusive, then this x square should go linearly in T, and for subdiffusive system, it should have a power law with the dynamical exponent less than 1. So if you look at the system with power, so please keep in mind that this is ongoing work, so we don't have data for very large system sizes here. Within the error bars, I will conclude that for the power system with power law interactions, there is this dynamical exponent beta is almost close to 0. And for the power law hop, you see that for alpha less than or equal to 2, it is non-zero. So it increases. This exponent increases as you increase the range of hopping. But the surprising thing is beta always remains less than 1. So you have a system with long range hopping, but still you get a subdiffusive transport. The subdiffusive transport people have seen on the ergodic side of MBL transition in systems with short-range interactions and random disorder. And generally, it is explained in terms of, again, rare region effects, because you might have localized patches even on the ergodic side, which basically prohibits your dynamics and makes it very, very slow. But we have a system which is not where we don't have fully random disorder potential, but it is a deterministic aperiodic potential. We don't expect those rare region effects there. And also the range of hopping is really large. So it's very surprising that we see subdiffusive behavior. So that's something we need to understand better. The first thing we need to do here is like going to the longer range hopping. I'm sorry, the bigger system sizes. Try to see whether it's a genuine effect or is it just that the wave packet is not able to spread. It very quickly touches the edges of the system and we are not able to see this. So now if you compare the dynamical exponents for from 3 different calculations, from imbalance, from return probability, and from the mean square displacement, so generally for a diffusive system, these 3 are related with each other with zeta equal to z equal to beta by 2. So we see that these 2 are pretty close to each other, in fact better than what we expected for these system sizes, but they are pretty off from the dynamical exponent you get from your mean square displacement. So this also shows that the transport is really anomalous, but why it is subdiffusive even in this long-range hopping system in the presence of in the presence of this aperiodic potential is really something we want to understand. So all this thing which I showed you is for the system which has all the single particle states localized. You can also change the parameter regime in your model and look at the system which has single particle mobility edges. And now to see many body localization, you really need to go to a very low density of the fermions. So we fix the density of fermions to be quarter filling, and then again you can do a quench. So this is the data only for the long range interaction. So this is the imbalance as a function of time, and you see that it quickly saturates after the initial rapid decay. And this is the return probability as a function of time. And again, you don't see any change as you increase the range of the interaction. This is another thing which is very, very surprising, that even when you have extended and localized single particle states, and here I was expecting that if I turn on the long range hopping, system should be able to delocalize at least more easily compared to the case where all the single particle states were localized. But here the effect of localized interaction seems to be even weaker. So one reason may be because to see the localization, we have to be in the very low density regime of fermions that effectively reduces the effect of interactions. So it's good to think of a model where you can have single particle mobility edges, but still we don't need to reduce the density of fermions. So let me just conclude. So we studied a model of spinless fermions in the presence of aperiodic potential. And I looked at the effect of power law interactions and power law hopping separately. And the coefficient of these terms are uniform. And what we see is that power law interactions do not disturb MBL. MBL can persist in the presence of very long range interactions. And it's the hopping term which destroys MBL very quickly when you increase the range of that term. There are some surprises, like why do we see subdiffusive transport in the presence of long-range hopping? Why the entanglement entropy shows logarithmic growth with time. And our results are consistent with this resonance count argument given in Sarang's paper, and also consistent with the recent work of Shtadi Roy and David Logan, where they did basically a mean field calculation Fock space, self-consistent mean field.
Yes, please.
Yes, maybe more a comment than a question. We have already discussed this between us, and you already answered to Sarang's question, but I think it's still maybe useful for the audience, I think, because I think people may have got confused and had an impression that there is some controversy between previous analytical results and numerics and what you say, and I think it's all consistent. Now I'm concerning the role of long-range interaction in a system with short-range hopping. Yeah? So in this model, the prediction that we have, and it's also the prediction of this in this paper. So when we, I mean this paper that you cited by Gutmann et al. And also by Tikhonov and myself, and it's consistent with earlier papers by Burin and by Norman Yao et al. Sarank is one of co-authors, is that condition is that the dimensionality should be larger than b over 2 plus 1. And this plus 1 comes from this multiple expansion. So for example, you have the Coulomb interaction, so just in simple physical terms. Yeah? If you have Coulomb interaction, so beta is 1, it's 1 over r. However, the matrix elements between sort of electron-hole pairs that it connects will be dipole-dipole interaction, which goes like 1 over r cube. Yeah? So the condition is that d should be larger than 3/2 in this case. And this condition, d larger than 1 plus beta over 2, cannot be satisfied in one dimension. Right? So therefore, if you just take one-dimensional model with fermions with short-range hopping and add power law interaction, it, according to this prediction, will not delocalize. That's exactly what you see. So to have it in one dimension to delocalize the interaction, you may have a random interaction. So in the moment you include the interaction with, say, random sign, or so then there is no, then the condition will be just d larger than beta over 2. And then, and this is what you very nicely see in numerics, and what we did. So what they also had numerics with a spin model, but in this spin model was alpha equal to beta. Yeah. So the model that you consider this hopping, the short range hopping would correspond to alpha equal to infinity. Yeah? And then the condition will also give b plus 2 over 2. Yeah? But if alpha is equal to beta, the condition will be d larger than beta over 2. So everything is consistent. Yeah? There is no inconsistency, no, and non-random interaction delocalizes, for example, in 2 dimensions. Yeah. So as I told you, that the condition is d larger than, say, Coulomb interaction, d larger than 3/2. And that's very important. Yeah. So it's in 2-dimensional systems. The prediction is that you will have strong power law delocalization effect due to Coulomb interaction. So it's not due to, not this weak sort of exponentially rare, it has nothing to do with this exponentially rare events. It's a strong power law delocalization. That's is relevant to experiments. All this. So I think, so in general, your statement is that long-range interaction does not delocalize. I think it's, as it's formulated, it's not exactly. So basically, the statement should be, in one-dimensional systems and non-random power law interaction. Yeah, that's.
Well, that's what I showed in the rest of the talk.
Yeah,
so I didn't want to fill up the conclusion page with all the details. But I agree with all your comments. So basically, we also see that if you have one-dimensional system and non-random coefficients of this power law, then it is localized for all range of interactions, which is consistent with what you had. But there were some numerical work from other groups in between, which were actually not very consistent. So. Yes, yes. And there was some paper by Shankar Das Sharma also, where they don't see localization. Shankar Das Sharma.
Okay, so let's see. Maybe we have a real question now. I mean, after this long comment. Yes.
So all your results are for the interacting system, right? All the plots, but what is known about the that quasi-periodic potential with long-range hopping, which is a non-interacting.
Non-interacting long-range hopping case. That's actually a good question. So yeah, so you can go ahead and study it. So actually, we didn't try to explore it. We directly went to the interacting limit.
Okay, any other comment? Well, that's not the case, so let's thank all speakers of this morning.